Yuan, can you try like share screen?
Sure. Yeah.
Yuan, can you try like share screen?
Yep, I'm sharing it now. Can
Sorry,
you see anything?
Yeah, I can see. I think I can see.
Okay, cool.
Nothing? You don't have anything?
You can probably see a picture of a panda. That's what I'm seeing on my screen right now.
Right, so the pizza will be coming soon. So maybe we should just watch it through the laptop.
Yeah. I think there's enough people. I mean, there's not enough people that we don't have to.
That's true. Hey, Miller.
How long is this talk?
Around 1 hour. Miller, do you have the Type-C connected to? Thank you so much.
It's the
Yeah, HDMI.
So this is only HDMI.
Oh, I can do it on a laptop.
Oh.
Well, but the Zoom is on my laptop.
Oh, yeah, because I don't have a connector.
I see.
If I get my laptop, I could just zoom in and use that.
Okay, that's fine.
Think about like
So most of the people are showing up in person in the classroom.
All right, interesting.
And we will have pizza.
Oh, nice. Okay.
Yeah, I'm still waiting for them to give me the connector. Yeah, that should work. Sorry.
I got mine just in case, but
That's not
no.
not type C. Yeah.
Yeah.
You should use your computer.
Yeah.
Hey Yuan, I think
Yep.
we have some issue about audio, so we probably will start at 12:10. So this seems okay.
Oh, in like 2 minutes. Yeah. Okay.
Minutes.
Yeah. Sure.
I think we can get started.
Okay.
So, hello everyone. So let's welcome Yuan, the CTO of Entropica Labs. So Yuan received his PhD on quantum computing from National University of Singapore. And after that, he has been co-founded and been the CTO of Entropica Labs, which is a Singapore-based quantum computing company. And now, so Yuan, is all yours.
Okay, thank you, Meng. Let me just maximize this. You can see the slides, right?
Yes.
Can you? I
Yes.
think that's a yes. Okay, awesome. Okay, so thanks for inviting me to give this presentation today. Thank you, Meng, for that. Nice to be here. Can't see you all, but nice to meet you as well. So this talk is something that I actually give to usually a school of business students who are interested in quantum computing. So it kind of combines a little bit of technical content with more kind of industry or enterprise oriented approach to things. But hopefully it's still interesting for everyone. So the topic is quantum optimization, which is of course one of the main touted use cases of quantum computers in the real world. That's what we at Entropica Labs are heavily focused on, optimization for quantum computing with quantum computers. And this whole notion of top-down and bottom-up explorations, which is in the title, maybe you're wondering what I mean by that. Hopefully that will become clear in the next few slides. So let me just briefly say a few words about Entropica. So we're based in Singapore. Actually, I'm back home in Scotland at the moment. That's why it's not a ridiculous time of the evening, I guess, for me that it would be there. But in any case, we're based in Singapore. Our vision is, quite a common one, I guess, in the quantum computing industry. Make quantum computing useful, right? So we know this is a technology that we all love. It has a lot of promise, but there's a lot to do before we actually can make it something that is actually of help or use in real world settings. Of course, there's many aspects to that: hardware, software, and many things. But we're a what you might call software and algorithms company. So we're not building hardware or anything like that. I should of course make that clear from the beginning. How do we approach the question of making quantum computers useful? Well, we think that one very important part of that is just to use the devices. So regardless of the fact that today they may be pretty primitive and not really capable of doing anything that you couldn't do on a classical computer much faster and much cheaper, we really believe that the only way to a very important element of unlocking the future potential of quantum computers is to grow with them, use them as much as we possibly can, learn about them as they evolve, make the algorithms and get as much of the hardware out of the hardware as we possibly can at any given time. So that's what we mean by doing the most with quantum computers today. Specifically, of course, our focus is optimization. We have kind of two prongs in our approach to this. One is optimization with quantum computers, and one is optimization for quantum computers. So the with part is something that you probably can imagine what I mean by that. That's using a quantum computer, running a quantum algorithm to solve an optimization problem. So that's maybe what you traditionally would think of as quantum optimization. The for part here, this is actually using expertise in classical optimization for many of the problems associated with quantum computing. So there are there's a vast array of challenges that lead up to actually deploying a quantum computation, especially a large one. And classical computing has to support and will support a lot of this. So optimization algorithms form a very big part of that. For example, you have compilation tricks, qubit routing, all these kinds of problems, which become really a challenge when you have very large computations. Also, if you think forward to, say, error correction, there's a lot of optimization problems associated with, extracting error syndromes, many things to do with the use of resources there that are actually classical optimization, or well, they are optimization problems that naturally, at least at the moment, you might use classical optimization for them. It might be that you use smaller quantum computers in the future to solve those problems, but for now, classical optimizations are powerful, and we should use them to help us. So this is the width and the for. But today I'm really going to speak about the width part, which is really the more kind of, I guess, conventional thing that people think about when they hear quantum optimization. So here I go with the top down and bottom up concept. So this really comes from the idea that when you're evaluating a use case for quantum computing, say, a customer or someone has come to you with a problem, there's really two ways or two categories of approaches or problems that you can consider. The first one is what we call top down, right? So think about this as, a customer comes to you, somebody comes to you with a very large optimization problem on an industrial scale today. And the question is, what would I do how would I run this on a quantum computer? So it's very, very clear that you wouldn't run this today on any device, right? Because it's large, it's complex, it's probably going to be several years before we have anything like the kinds of technology that could even begin to tackle these kinds of very large, complex problems. But what the goal here is to really think, okay, well, which algorithms would you use? What are the trade-offs in using different algorithms? How many qubits would you need to actually run this problem, physical as well as logical? The resource estimates and so on. So basically trying to get a ballpark estimate for how long in the future you might be able to actually attack this problem with a real quantum computer. So this is the top down, because it's coming from very large problems, and you're saying, how do I run this on a device? The bottom up part is more like saying, well, okay, today we have a few tens of qubits, maybe over 100 now, just breaking into the low hundreds with IBM's recent announcement. What can we do with these devices? I mean, we presumably can't do much that's of use to industry right now, but we can start to play with these things, and we can start to use them. We can start to test the algorithms. We can start to test the workflows. We can start to, begin to try to see how the technology is evolving over time. If we have 100 qubits today, maybe we have 1,000 qubits or so in a year or two, according to some roadmaps. How is the hardware actually evolving if we want to run, say, benchmark problems or benchmark algorithms? So this is something that is also a very valuable approach to quantum computing, not just for companies like us, but also for enterprises, forward-looking enterprises who are really interested in really advancing with the technology, understanding what the state of the art is, the limitations, and so on. So this is what I mean by top down and bottom up. If it's not clear so far exactly what that distinction is, then hopefully it will become clear in the rest of the talk. I'm going to give one example of a top down problem that we've worked on, and one example of a bottom up problem that we've worked on. Okay, so let's dive straight into the top-down approach. So here, what I'm going to try to convey is two notions or two ideas. One is that there are definitely dead ends. So what I mean by that are use cases where you're probably going to conclude that you would never use a quantum computer. We know that they're not going to be good for every problem out there, and we've found a use case where we certainly concluded that there would probably be no point in using one. And I'll give some idea of how at least we approach the idea of thinking about where are the more promising use cases, the promising avenues for finding applications that at least seem to be more likely to be amenable to quantum approaches. So this is the dead end. This is a project that we worked on with BMW, who I'm sure you all know is this very large German car manufacturer. The problem that we worked on together with them was ride hailing. So you probably know what that means. That's Uber, Lyft, or whatever the local equivalent is. You have passengers who are requesting to be picked up from some pool of taxis or private cars. They're using their phones or whatever to request these pickups. And the way this is an optimization problem is typically that the provider would batch together requests that come in over, say, a period of maybe 30 seconds, and then they would run some optimization algorithm. So the goal for them is typically, it can depend on the particular operational objectives, but typically they're interested in something like minimizing the distance that the taxis have to cover. So that means, of course, reducing the fuel costs and minimizing the time that passengers have to wait before they get picked up. Okay, so nobody wants to be standing there for 20 minutes before they get picked up. So typically these are, the first one is kind of efficiency. The second one is customer satisfaction. There might be other objectives, but these are two of the most common ones in this setting. So on the face of it, you would say, this sounds like an interesting problem for quantum computing, right? It's economically, it's quite an impactful problem. If big cities, you can imagine that lots of people are generating lots of requests. Companies like Uber make lots of money. There are lots of people using their services, and it kind of has the flavor of a typical logistics or planning problem. But you scratch the surface, there are several problems with using quantum computation for this use case. So I'll go into what the three major roadblocks that we identified are. So the first one is maybe the one that you would think was most obvious, that we only have a limited time to actually come up with a solution to this problem. So the optimizer basically has to run its course within this 30-second time window. And by the way, 30 seconds is maybe actually too long for many operators. It might be shorter than that. It might even be 10 or 15 seconds or something, but it's of the order of, half a minute or some fraction of a minute. So you might think, well, hang on a minute, but aren't quantum computers supposed to make things faster? Well, there's a subtlety there that hopefully will also come out later in the slides. What do we mean by speeding things up? In what cases could we expect to speed up? But basically here, I mean, you can kind of work through what the problems or the obstacles might be to solving this problem in say 30 seconds. So if you think about variational algorithms, so I assume that people here have a kind of heard of variational algorithms and maybe have some working knowledge of what they are. So for optimization, you would typically say, let's use QAOA, right? It's a quantum approximate optimization algorithm. So what would we need to do to solve this problem? Well, of course, it's an optimization algorithm, so it has many iterations, right? So you have some parameters that you throw into the QAOA, which need to be updated through this kind of classical quantum loop. And eventually the thing will converge to some solution, but it's not going to happen presumably in a very small number of iterations. So this is going to take some time. At each iteration, to get the cost function for this parameters that are being used in the current iteration, you need to take many shots, right? You need to build up the statistics to get the mean value of the cost function. This means you need to run the circuit many times at each iteration. And on top of that, the classical parameter updates, depending on the number of parameters you have, can become a very big bottleneck as well. So yeah, and I should mention on the previous point, the number of shots is also quite a challenge in the variational setting. So as the problem gets larger and larger, typically you need to take more and more shots because we don't have the luxury of running things like amplitude amplification or things like that. So this notion of like the number of measurements that we need to take in variational algorithms is also a big bottleneck. So you can do some back of the envelope calculations for this use case. In the most kind of say hardware friendly encoding for the problem. Hardware friendly meaning that you keep the problem as a quadratic optimization problem. You don't have many body terms in the Hamiltonian, which I'll come to that in a second. The number, if you have a problem, say with 20 passengers and 30 taxis, the number of binary variables that you would need, so that's also the number of qubits, is of the order of something like 9,000 or 10,000. And you can do, you can make some assumptions about what the hardware would be. You could say, let's use the superconducting chip, because those are typically the fastest on the market. Get the gate times, assume some connectivity for the device. Let's be favorable to the hardware and give it full connectivity. It's actually very challenging if you do this kind of back of the envelope calculation to even see how you could do a p=1 QAOA to anything like a reasonable number of optimizer iterations. P=1 means just one layer of QAOA with just two parameters. So for a problem of that size, it seems highly unlikely that p=1 would be sufficient to solve the problem. So without over bashing on about this, the time here is really an issue, and the time also shows up with fault tolerant algorithms as well. This is not just an issue of variational algorithms. You still have the problem if you were to try to run Grover's algorithm needing to take many shots. The time that is required to implement quantum error correction is also extremely a big consideration, and it's hard to see that for a problem of that size how you would do it in such a short period of time. So this is the first issue with the use case. The second issue, I've kind of mentioned parts of this already. This objective function is actually quite a complicated one. So we want to minimize not just the distance, but also the passenger waiting time. The passenger waiting time is actually quite a pain in terms of what the objective function looks like. And the reason is quite simple. I don't know if you can see my mouse, but if you just follow, say, this red in the figure on the left here, there's this kind of red colored path. It starts kind of in the center, kind of just a little bit up to the left of the center here. What it's showing is basically a taxi which starts in some position. It goes to pick up a passenger at this location which says P2, and then it goes to drop the passenger off at this position D2, and then goes to another position P0, and then it drops the passenger off right in the top right of the figure in this position D0. So the waiting time of the second passenger depends on what happened, what the trajectory of the taxi was in picking up the previous passengers, right? So what this means is the cost function has this kind of precedence dependence. It really depends on the ordering of how you choose to do things, and this becomes a real pain in encoding the problem. So there's two approaches. One is to say, well, let's assume we just have time steps. So, we say for every taxi, it has many possibilities. It can go and pick up passenger 1 and drop passenger 1 off, or it can go and pick up passenger 2 and drop passenger 2 off, or it can go and pick up passenger 3 and drop passenger 3 off, and so on and so forth. And you do that for every taxi. And you have a decision variable, a 1 or a 0, basically saying, which of all of those possibilities you actually choose. You can see how this very quickly scales up in terms of the number of qubits, right? So those decision variables would each be represented by 1 qubit. So that really begins to kind of explode in terms of the number of qubits. The benefit is that the cost function does remain quadratic, because to evaluate it, then you only need to basically look at which path segments are crossed, individual path segments. This is maybe a little bit hard to see without actually writing it down on paper, but you can kind of just kind of believe me that if you do things this way, the cost function, the Hamiltonian you would write down, would basically be a sum of basically two body operators, two Pauli Z's, essentially, quadratic terms, and the sum of these would give you the total waiting time, and the total path would just be a sum of whether you choose to go from A to B and then B to C, or you do A to B and then maybe B to D or something like that. But the total energy, or the total waiting time in this case, is just the sum of those individual segments. But this blows up in terms of number of qubits. On the other hand, you can keep the number of qubits to a minimum, but then you need a much more complicated cost function, which is actually able to read an entire path and assign a number to that path, a waiting time in this case. But that operator needs to be many-body. It needs to be able to read, okay, so we go from A to B to C to wherever, and it needs to have, as many operators in the polynomial term as locations that could conceivably be visited by the taxi in sequence. So yeah, this is another big roadblock to implementing this in the near term. So what I mentioned on the previous slide was actually, with this 9,000 variables or something, was assuming that you have this time steps approach where you just have many more qubits. It seems more likely that we can have many more qubits in a reasonable time scale than to be able to perform, say, very complicated, multi-qubit operator terms, which would have to be actually broken down into basically two-body operators, unless the hardware itself supports many-body operations. Okay, so that's the second issue. The first issue was the time limitation of the use case. The second issue is the fact that the objective function is very complicated for near-term hardware, at least. And the third issue is actually that classical algorithms are pretty good for this problem. So they can perform fairly well, and they can do so quickly. So before we even began this project, the BMW team had explored meta-heuristic approaches. So these are approaches like taboo search, which are able to, they're not quite, I wouldn't say they're quite global optimization techniques, but they are able to explore, they're more powerful than simple heuristics like greedy algorithms or something like that. And they had applied meta heuristics to this problem and found some, pretty reasonable results. But something that we were also able to do in this project is to come up with a problem-specific heuristic. So this was an algorithm, a heuristic algorithm, which was a classical heuristic algorithm, which works for this use case specifically. It's actually quite easy to explain the basic idea behind this problem specific heuristic. So if you think about this ride-hailing use case, there's this number floating around, there's this ratio floating around in the problem that actually determines how complex the problem is. And it's the ratio of the number of passengers to the number of taxis. So if we have many taxis, but very, very few passengers, then it's pretty clear that the best thing you can do is just to send one taxi. Well, each passenger should be serviced by one taxi. So if there are 4 passengers, we just send, 4 taxis, one to each of the passengers. That minimizes the waiting time, right? In this limit, it's actually it becomes a problem that is a textbook operations research problem. It's called the assignment problem. And there are already, it's one of the most common algorithms in operations research. So there are algorithms that people have worked on, back in the 50s or 60s or whenever, which can solve this problem, and they can actually do so exactly in polynomial time. So that of course means that it's not especially a compelling use case for quantum computing, right? If you have an exact polynomial time algorithm, then unless the problem is extremely large, you're probably going to stick with classical algorithms. But in any case, for this use case, there's an acceptable waiting time, which really, you can imagine a passenger somewhere in a city, and you could draw a radius of about 10, equivalent to about 10 minutes around that passenger. And you would say, well, we don't want any passenger to wait more than 10 minutes. So we would never send a taxi, which is on the other side of the city, maybe half an hour away, to that passenger, right? So you can actually kind of imagine that this problem is susceptible to kind of decomposition into smaller sub-problems, if you like. So in any case, this use case is not necessarily likely to become very large in practice in terms of size. Now, where the problem becomes hard is in the limit where you have many passengers and few taxis. So the number of taxis is smaller than the number of passengers. That's where the combinatorics really starts to come in, right? Because in terms of the waiting time, it really matters the order in which the taxis begin to execute the trips, because then you might end up with the last passenger is waiting an extremely long time compared to if you had a better solution. The interesting thing is that we were able to basically take this simple algorithm, which operates in the small number of passengers regime, and sort of bootstrap it up towards the regime where there are more passengers than taxis, and you get some kind of approximation to that. So the details of this slide, of this figure, don't necessarily matter too much. We're just comparing a bunch of different approaches to this problem. Everything is basically being normalized to a greedy solution, which is this black line here at number 1. On the y-axis, this is the waiting time that a passenger needs to endure. This is the time that the passenger has to wait on average, compared to the estimated waiting time, which comes from the greedy algorithm. And basically, this kind of brown colored line here is the custom heuristic that we came up with, where as you push the ratio of, or the number of passengers to the number of taxis, as you increase that ratio towards 1, our custom heuristic was actually performing very well compared to most of the other things that we considered, and it was doing so much faster than all the others. This red one is a simulated annealing algorithm, which also does well, but it takes a lot longer. So we were able to come up with this custom heuristic, which actually performs pretty well. The other message was that there's a better classical algorithm or a simpler heuristic floating around there that hadn't been discovered yet. So maybe the message there is that when you undertake these kinds of studies, you can see classical computing maybe as your competition. You're trying to beat classical computing, but at the same time, it's also an opportunity, right? It's an opportunity to come up with new ideas, and if in the case it's a customer, you can give them a solution that they didn't have before, and that could potentially be very interesting for their business operations. Okay, so maybe I'll stop and ask if there are any questions at this point before I go on. Okay.
Hey, thanks. I've got one question real quick.
Oh, that's awesome.
Sure. Yeah.
Okay.
Do you want to maybe type the question or something? Or we can maybe return to the question at the end. Is that okay if we just return to the question at the end and I just continue? Can you hear me?
Yes, we can. So we can come back later.
Okay, let's do that then. Okay, so like the previous section was very much a deconstruction of a use case that doesn't seem to have any particular promise for quantum approaches. But how might you go about identifying useful, like more promising use cases? So there is a bit of an asymmetry here. Of course, I can tell you a lot more about the use cases that we've found that don't look promising. I can't tell you too much about the use cases that we think look more promising at this stage because of confidentiality and so on. But I can give some hints of how we think about identifying use cases which are more likely to be amenable to quantum approaches. So I like to rest on IBM's. They have these. Maybe you've seen these stickers that they give out at conferences, where they have this mantra of like, you're thinking too classically. You should think like a quantum physicist. It's great. We all love quantum computing. It's marvelous. Yes, we should think more. Quantum computing definitely requires a kind of shift in thinking from classical, but for these kinds of use case studies, you actually need to think very, very carefully about what is possible classically. And it's not really a massive revolution, right? But it's one of the best things you can do for yourself in trying to identify promising use cases for quantum computing, is to say, is this a good use case for classical computing, or is it really hard for classical algorithms? So, in fact, you can actually think like a physicist here as well. Or a mathematician, I suppose. So, given any problem, what do you do as a physicist? You try to understand the theoretical extremes, right? So, try to identify if there's any parameter floating around the problem, which can be adjusted and sent to 0 and sent to infinity, just like I explained in the previous slides with this number of passengers to number of taxis ratio. If you can identify some parameter like that, depending on where it sits, you have one solution or another solution, one regime or another regime. Maybe in one regime, a classical algorithm works really well, and the other regime, there's a lot of difficulties there in solving the problem classically. Thinking like this really begins to help you identify the structure of the problem and where, if any, place at all that quantum computing could fit the problem. Can it be reduced to some other problem, right? This is a very common thing in optimization. In particular, you try to say, well, okay, I have this problem, but if I were to relax it a little bit, it might look more like another problem. So for example, the vehicle routing problem, which is shown here on the right, you have a bunch of trucks which are going around a bunch of cities, and they have to return to the depot. And your goal is to basically try to minimize the distance that the trucks travel and potentially minimize the number of trucks needed. On the left there, you have the traveling salesman problem, which is obviously in some limit just a reduction of the vehicle routing problem. And the traveling salesman, of course, is one of the most studied problems in computer science. And there are many, many algorithms, many, many heuristics that have been developed for it. So if you can gain some intuition about how to solve the vehicle routing problem from the way that people have solved the traveling salesman problem, that can also be very helpful. This is another thing. So lower bounds or upper bounds are an incredibly informative and important thing to compute, and they're often very easy to compute. So for the traveling salesman, what would be, so we know what the traveling salesman problem is, right? It's, a salesman has to go around a bunch of cities and come back to the starting point. And the question is to find the order in which he should go through the cities in order to minimize the distance covered. Now, what would be an absolute minimum distance that the salesperson has to travel? Well, one thing that certainly he has to do is leave every city, right? That's obvious. So we can get a very simple lower bound on the distance by simply saying, okay, well, if I have to leave every city, what's the smallest distance possible that I would travel on leaving that city and going to another one, on every city and going to any other one? So for example, in this is a distance matrix for traveling salesman. So you can see for leaving city 1, the shortest path takes you to city 5, and that's only, say, 1 kilometer. Leaving city 2, if I look through this row in the matrix, the shortest distance I would travel is 3 kilometers. Leaving city 3, I would go to city 1, that's also 3 kilometers. If you basically add up these numbers, you get a very crude lower bound on what the distance of the salesman has to travel is. Now, this is not a feasible solution, of course, because you can see it has a cycle, right? It tells the salesman that he would have to leave from city 1 to go to city 5, but then city 5 is telling him to go from leaving city 5, he has to go back to city 1. So this is not a feasible solution, right? It has a cycle, so it doesn't fit what the notion of a traveling salesman path is. But at the very least, it gives us a lower bound. And this is an important point, because in your evaluation of whether a use case is going to be amenable to quantum, this is maybe also not really just about quantum computing, but about the use case itself. You have to ask yourself, okay, this is the lower bound. if I run some simple algorithm, say a greedy algorithm, or maybe I run simulated annealing for 15 minutes or something like that, I can get this solution. Then you're going to find some gap between what the lower bound is and what the best solution you can easily come up with is. And you say, okay, well, that gap, maybe it's 3 kilometers or something like that in this case. Then you have to ask yourself, is it worth my while to go off and try to find a quantum computing approach to solve this problem for those potentially 3 kilometers that I could save? Is it economically viable to do that, given all the time and all the money I would have to spend to find the right quantum computing approach, run it on a quantum computer, and so on? And this lower bound is, of course, not likely to be the optimal solution either. It's likely to be higher than this. So if you see 47, maybe the actual lowest, the shortest feasible path is maybe 49, I don't know, 48 or higher. So if your greedy algorithm is giving you 50, you might say, well, okay, is it really worth me saving, going to all this effort to save 3 kilometers? So it's an important consideration. I think considering classical algorithms as well is just a very important thing. So you have exact algorithms, you have heuristic approaches. Gain an understanding of what these approaches are for your problem and try to understand how well they perform. What's the runtime? So if you have an exact algorithm, what's the runtime of this exact algorithm? So it might be, usually we're talking about NP hard problems, right? These are typically what we're trying to solve in these cases. But there are NP hard problems and there are NP hard problems. For example, the knapsack problem, which is one of the kind of classic textbook optimization problems, is what's called a pseudo, it's a weakly NP hard problem. So this means that the complexity of it depends on some numerical input to the problem itself. In this case, it depends on the maximum weight that the knapsack can take. If you're not familiar with the knapsack problem, it's basically you have a bunch of objects that you can put into a knapsack, a rucksack. They each have a weight, they each have a value. You want to maximize the value of the objects that you put into the knapsack, but make sure that you don't exceed the weight capacity of the knapsack so it doesn't break. There is actually a dynamic programming algorithm that gives you an exact solution to the knapsack problem. And the runtime of that depends on the weight capacity itself of the knapsack. So what you have to do is go off and say, well, okay, in a real world case, what would be for the real world case that you're examining, what is the weight capacity? And what would be the kind of ordinary runtime of the dynamic programming algorithm in that case? Because if it's not that bad, then why would you consider a heuristic algorithm, classical or quantum, when you already have an exact algorithm, the dynamic programming algorithm, which has a decent runtime? And of course, industry solvers like CPlex, which is an IBM product, are also quite good for benchmarking against when you're trying to figure out how well classical algorithms can perform. CPlex typically runs integer programming methods, but it's widely used in industry, so it can serve as a good benchmark as well. If I'm to try to kind of summarize the last few slides, maybe one way to look at it is in terms of this picture here, which I'm showing. So in optimization, or I guess in any domain, for an algorithm, you typically have this trade-off of runtime and problem size, or required accuracy, but let's just stick to runtime and problem size. So ordinarily, the runtime will increase as the problem size increases. There are very few problems or algorithms that can run kind of in constant time or very low runtimes, which are actually interesting. The runtime typically increases with the problem size. And so classically, you might have some curve like this. Now we know quantum mechanically we have algorithms which can perform faster than classical algorithms. Grover's algorithm is a good example of that in optimization, for example. So you get a quadratic speed up over classical approaches. So these curves actually, there is a kind of quadratic speed up here, but there's an overhead to using quantum computing. This comes from the fact that typically quantum computers, the operation for operation are slower than classical computers. The gate times are slower. We have to do a lot of work to deploy things like quantum error correction, for example. We have to take lots of measurements to get cost functions and things like that. So there is an overhead to applying quantum computing in the first place, even though in the long run, kind of asymptotically, there is a benefit. So you can see how this affects, for example, going back to the case of ride hailing, use cases where you have a very strong constraint on time. So you're demanding that you have a solution in a very short period of time in ride hailing, for example. And that's going to typically lead you to the conclusion that, well, I might not even be able to get a solution using a quantum algorithm in such a short period of time. So the only alternative is to use a classical algorithm. If you have a much more flexible use case in terms of the time, you don't mind waiting a few hours or a few days for a solution, this would typically be maybe more something like advanced planning, where you have to get the decision right, because you're going to do something drastic afterwards, like build a factory or build a network or something like that. So it's okay to spend a lot of time optimizing, and then based on the result of that, you go off and take some action. These use cases are going to be more compelling for using quantum approaches, because this is where you're going to start seeing the benefit of this quantum speed up. And you can also see in this picture what happens if you have a classical algorithm, which you find a better classical algorithm, it will typically shift this blue curve down. So the time that classical algorithm needs will come down in the y direction, and it will push this crossover point further out. So it makes quantum algorithms a bit less compelling. So this is just a kind of pictorial representation to try to illustrate some of the ideas from the last few slides. But basically, I would say that good candidates for quantum approaches, use cases for quantum approaches, are these ones where you don't have really unrealistic constraints in the operational setting, where you're asked to come up with a solution in a very short period of time. There has to be a room for improvement, right? So that goes back to the idea of these lower bounds that I was saying. So you're trying to work out there the economic case for applying quantum computing and saying, well, okay, with a classical algorithm, I can already get to, say, 50 kilometers. The lower bound is 47 for this traveling salesman problem. The best I could do is to get a 3-kilometer improvement. Does that make sense economically for me to try to use a quantum computer to solve it? Yeah, and the last point about unsatisfactory performance of classical methods kind of goes hand in hand with some of these previous points. So you don't want cases where you can already do very well with classical algorithms, either whatever they are, heuristics or things like simulated annealing or genetic algorithms. If these things perform well, it's going to make the argument for using quantum approaches more difficult. Okay, so that's the end of the top-down approach. Just see how we're doing on time. Okay. I will continue with the bottom-up approach, unless I don't know if the audio is fixed, if anyone wants to ask a question now.
I think we have got a question in the chat box.
Ah, okay, let me check. Ah, okay. Quantum inspired. So the question, okay, let me, I know there are several use cases. So I think what you mean here is maybe like the dequantized algorithms. So I should say that quantum inspired has a bit of a, it's a term which has many meanings. So maybe the one that's kind of prominent in many people's minds is dequantized algorithms. So these are algorithms which, you know, like the quantum recommendation systems algorithm, which was published with a lot of fanfare a few years ago, which basically applied something like an HHL exponential speed up to the question of you know, the recommendation systems problem, Netflix or whatever. But famously, this was dequantized by Ewan Murno. Basically, a classical approach was found, which has essentially the same scaling in many of the important parameters, well, primarily the problem size, as the quantum approach. There are caveats there about, you know, the sparse, some of the constant factors look really bad in terms of accuracy and so on, and error. But nonetheless, a classical algorithm was found, which has the same intrinsic scaling in terms of problem size. So this is one meaning of quantum inspired. So taking a quantum algorithm and looking at it and saying, okay, could we try to do the same thing classically? Maybe, okay, I guess it's kind of related, but maybe it's taken on its own meaning as quantum inspired optimization, which is being pushed as a service by, you know, some companies now. Yeah, the idea here is to try to leverage effects that look kind of like tunneling, for example, in classical Monte Carlo based algorithms. So actually, typically these come from trying to simulate quantum annealing. So simulated quantum annealing is maybe a good example of a quantum inspired classical algorithm for optimization. People were trying to understand how they could compare the performance of quantum annealers to quantum algorithms, to classical algorithms, which are kind of doing something similar. And then there was a realization, I guess, at some point that, hey, okay, we could also just use these classical algorithms, which are simulating quantum annealing, to also solve real world optimization problems. So that's another meaning of quantum inspired. There are other things that you might say are quantum inspired, like tensor networks. Things like that are also kind of, maybe you could say that they're quantum inspired. But I think if I'm coming back to the question, the approach, the algorithm that we came up with for the ride hailing wasn't quantum inspired. No, it was just looking at the structure of the problem and coming up with a heuristic that worked for it. Yeah. Hopefully that answered the question.
And then we have another question coming in.
Okay, let me see. Okay, in the previous chart, you mentioned that slower gate time operation and needed for error correction increases time complexity. Yeah, would you expect this to get reduced in the future with better hardware in terms of higher quantum volume? I think gate times, I mean, I assume physics comes in at some point to limit gate times, right? So I think that, I mean, I believe that they could be improved in some systems, but ultimately I think that there are physical limits to how fast. I mean, you know, typically something like the lifetime of a qubit would set, of course, some physical limit on how fast a gate could be. If you have, I mean, I guess if you have super fast gates, you'd be thinking about like ultra fast pulses, right? But the problem with ultra fast pulses is that they're made up of many frequency components, and then you might start coupling into transitions in the qubit or atom or whatever that you don't want to, and it no longer it might stop behaving as a good qubit, and it would be like some multi-level system. So I think there are physical limitations there in many cases. And about error correction, I'm not really an expert on that, but I mean, I think that that problem is never going to go away. It might get better as the intrinsic error rates get lower, and you need to use fewer qubits, say for your error, for a particular error correcting code. The overhead becomes lower, for example, to do quantum error correction. That might get better, but it's not likely to. It's not going to go away, that problem. There was a paper recently by, fairly recently anyway, by a group of, well, a bunch of researchers. The one I remember was Nathan Wiebe, was one of the authors. I can maybe share I'll have to dig it up and see. It's quite a long paper about basically prospects for quantum optimization when you have fault tolerant but small fault tolerant quantum computers. So maybe, you know, when you have a few hundred logical qubits, and they examined some of the potential for using these for specifically quantum optimization problems, and they do discuss quite in detail all of these kinds of things. So I can maybe share that with Ming, and that can be shared with the rest of you. Yeah. Okay. If there are no more questions, then I'll just move on to the next part of the talk. So so this is bottom up. So as I said earlier, this means now we're looking at things from the other perspective, where we're saying, rather than here's what I want to do with a quantum computer, tell me how to do it. This is like, here's a quantum computer, what can I do with it today? Basically, that's the difference. So the way I'm going to tell you about a project that we've done, running it's been quite fun running some quantum computations. The angle that I'm going to take on this is to consider what can you do on a budget with quantum computing today. So again, this is kind of motivated by the question of, imagine you're doing a POC, or you've got some kind of, you've been given credits by some hardware provider, for example, which is, they're actually, many of them are giving credits to researchers at universities and so on to play around with the hardware today. So the question is, whatever the case, whatever the situation is, there's going to be a budget, right? And how does this budget, the cost of quantum computing, actually affect what you can do in this kinds of, POCs? POCs is proof of concept, by the way, if you don't, if that's something that's familiar to you, or kind of toy research benchmarking projects. So you probably know that quantum computing is quite expensive compared to classical computing. That's true today, for sure. And one effect of that is that if you're doing benchmarking studies, so imagine you're trying to say, well, I want to test the performance of this algorithm, or I'm interested in, seeing how well this hardware can solve this problem using this algorithm. It limits simply how many problems you can run, right? Ideally, if you're testing the performance of an algorithm, you want to run maybe several or many problem instances to get some kind of idea of the average performance of the algorithm. This is the way that things are done a lot in classical computing studies, but with quantum computers today, because of the fact that it costs a lot, you're kind of limited by limited in the number of problems you can actually run and test your algorithm on. And in the future, you can only imagine this is going to get a bit more acute as a problem, because by the time we get to 50 qubits, or in practice, actually, maybe 30 or so, it becomes extremely challenging or impossible beyond whatever, 50 or 60 or something like that, to simulate a quantum computer on a classical computer. So a lot of the work that we do today, developing and prototyping algorithms, testing lots of things related to the algorithm, seeing if things make sense, we do a lot of this stuff on simulators today, right? But by the time you get to, let's say, 40 qubits, in practice, unless you have access to a very large supercomputer, you're not likely to be able to do that. And development is going to presumably shift directly to running things on the QPUs, which again means that we're going to be paying more, because it's not just we test on the simulator, then we run a few small computations on the QPU. It's going to be like we have to do a lot of our prototyping already on the QPU, and that carries the cost implication with it. So the question that we asked ourselves was, okay, let's just try to fix a budget, and see what we can do in the setting of quantum optimization to solve an interesting problem today. So we set a budget of $2,000. That's maybe in the ballpark of what you might get as credits from AWS or from Microsoft or whoever, or maybe the hardware providers directly, if you get some kind of research credits for them, which some of them are definitely giving out. It's also conveniently kind of like the cost of if you want to rent a virtual machine on the classical cloud, dedicated for yourself, maybe 72 or 96 cores, something like this. It might fall into that kind of ballpark of cost. So it's kind of interesting as a yardstick for what you can do with classical computing with such a budget. So what we wanted to do was to basically take a problem and look at how the budget impacts what you can do as a hardware, as an algorithm developer, on different devices. So on AWS, this is work that we did through the AWS Bracket service. We accessed the IonQ device, which has 11 qubits, the Rigetti device, which has 32 qubits. And basically we wanted to see how does this budget affect what we can do as algorithm developers? What trade-offs are we going to have to face? So as I said, we're interested in optimization problems, and we took maybe one of the most prominent optimization problems that you can imagine. It's a very common optimization problem, shows up in many industries, in many settings. It's a good textbook problem in the real world. Maybe it shows up not exactly in the way it shows up in textbooks, but there are many related problems in the real world to this kind of core problem class, which is bin packing. So the idea here is basically that it's quite similar to the knapsack problem that I mentioned earlier, but it's not exactly the same. So here what we have is a bunch of objects, each of which has a weight and we have a set of bins. And what we want to do is to place these objects in the bins such that all of the objects are put in a bin. We use as few bins as possible, and each bin has a capacity, so we can't overload the bin with excess weight, right? So this is the statement of the problem. We want to minimize the number of bins, subject to these constraints that all objects have to be assigned to a bin, and no bin should have more than this capacity C. So these are the weights that we used for this particular instance, and we set this weight capacity here to be 10,000. Okay, this was, we cooked up the problem with these numbers, and kind of mirroring a little bit what I said earlier. Of course, when you see something like this, you might want to ask yourself, what classical algorithms are there that we can use to solve this problem? For bin packing, because it's one of the most famous optimization problems, there are a ton of simple heuristics that you can use. Some of them are listed here. They're called next fit, first fit, best fit, worst fit. You can go away and look up what these actually mean. But basically, if you run one of these, I mean, these things return a solution in a matter of milliseconds or less. The best result that we found running all of these required 5 bins. Okay, so that's just a kind of yardstick for this problem. There are 16 objects. You can actually compute an upper bound as well. So you can compute upper and lower bounds. The upper bound basically, the upper bound basically comes from kind of summing up all of the weights and basically trying to see, you relate it to the capacity, and you basically, out of that, you can see what the absolute maximum number of bins that would be needed. There's a similar procedure for finding a lower bound, which in this case is 4. So the simple classical heuristics don't reach the lower bound, but in principle, we don't even know if the lower bound has there's a feasible solution with this lower bound that uses 4. But we ran simulated annealing, and it actually did find a solution with 4 bins. So we ran simulated annealing for long enough that it actually found a solution with 4 bins. So we know that that solution is optimal, and it's kind of shown over here. So a very simple classical heuristic gives 5 bins. Simulated annealing gave 4 bins, and we know that that's an optimal solution. Okay, so this kind of acts as like a, an example of some of the stuff I was saying in the previous part of the talk, setting the context for the problem and understanding what classical algorithms can do. Okay, so this is an optimization problem. We're going to go off and run this on a near-term device. So surely we would be using QAOA, right? I mean, that's the only game in town, right, for optimization. Actually, it's not really. It's actually not going to be possible to run this problem with QAOA, at least on the small devices that we have available. It might be possible on IBM's new device, if they could add 1 more qubit to it. The reason is that in a very simple binary encoding for bin packing, if you want to keep the problem quadratic, in contrast to having multi-body terms in the Hamiltonian, if you want to keep everything kind of quadratic, then you need n times m qubits. So n is the number of objects, which in our case is 16, and m is the upper bound on the number of bins, which is 8. So we would need 128 qubits to solve this problem using QAOA, assuming that we're using quadratic Hamiltonians, which of course is beyond what we have certainly on the IonQ and Rigetti devices. As I said, if IBM were to add 1 more qubit to their latest device, maybe we could manage it. But at the time we ran this was certainly not a feasible system size that we could access. So basically, the algorithm here, by the way, is not really the important point. I'll just say that. So I'm just giving some details of how we ran this, but we're not claiming that this is an algorithm that anyone should use to solve the bin packing problem in practice. But it was just it was a way that we could solve the problem on the hardware today, and solve a non-trivial instance of the problem. Of course, you could cook up like a problem with 2 bins and 2 objects or something, and maybe you could fit it on a device using QAOA even. But we wanted to do something a little bit more interesting, and so we had to work around a little bit and try to find an algorithmic approach that would work. And yeah, but I would say that certainly this is not a scalable approach for quantum optimization. But for interest's sake, the way that we used the algorithm that we used really kind of trades space for time. So instead of using 128 qubits and having kind of a qubit encoding, if you like, where every binary decision variable in the problem is encoded in the state of a particular qubit, we go for a different encoding where we use far fewer qubits. We actually use 6 qubits here. And the information that we need is actually in the amplitudes of the output probability distribution. So the circuit, this is what a layer of our circuit looks like. It's just a bunch of RY rotations with these angles, theta 1 and so on, and some entangling gates, CZ gates. And then this kind of repeats for, we actually just use 2 layers in this, in the QPU computations. And the way that the correspondence between the binary decision variables of the problem and our the basis states of the quantum computation is basically you would read out you have outputs output states which can look like this. So some of the qubits can be in 0, then you have 1 1 0. This would represent the number 6 in binary. So what that's going to represent is the 6th decision variable in our optimization problem. And then we basically digitize the probability distribution. So you look at the probability distribution, you have some threshold, and you say if the probability of 0.00110 is above this threshold, then I'm going to say that the variable x6 takes the value 1. If it's below that threshold, then it's going to take the value 0. That's basically what the algorithm does. It's not scalable really because we're talking about measuring the probability distribution to get the information we need to extract a configuration. So if you have to measure the probability distribution, that kind of grows exponentially, right, in the number of qubits. That's why I said it trades space for time. But this allowed us to at least solve the problem today, because with 6 qubits, you don't need to make so many measurements. You can get away with a few hundred or 1,000. Okay, so that's the kind of variational circuit. Of course, there's a classical optimizer which has to go with that, and this is actually what we're going to explore in terms of the trade-offs of cost. So the optimizer we used is something called SPSA. So this means, if I'm not mistaken, stochastic perturbations or simultaneous perturbation stochastic approximation. Doesn't really matter what that means. The good thing about SPSA is that for each function evaluation you make, for each iteration of the optimizer, you only need to take 2 function evaluations. This is in contrast to, say, a gradient-based method where you might need to shift every possible parameter in your circuit, by a plus and a minus, depending on how many parameters you have. That can quickly blow up into many function evaluations for each optimizer iteration. But SPSA is very kind of economical. It only requires 2 of these 2 function evaluations. Basically, it shifts all of the parameters together in some stochastic way. So it's kind of economical, and the stochastic, leads, I think, people to believe that it might be a reasonable optimizer for noisy optimization settings like quantum sampling from quantum devices and solving problems on quantum computers. So so we use SPSA. We fixed the number of iterations of the optimizer to be 100 as a maximum, and we took 1,000 shots at each iteration to get the statistics we needed to compute the cost function value. So these are again just numbers. The upshot is that what we reach is this kind of 2,000 ballpark figure for the cost of running this entire process on the IonQ device. So this $2,060, what this means is we can run one problem for 100 iterations of the optimizer using our variational circuit, where each time we use 1,000 shots, 1,000 measurements to build up that probability distribution that I mentioned to extract a single bit string, which then is the cost for each optimizer loop iteration. Sorry. Okay, so on IonQ this costs $2,060 at current prices, and on Rigetti it actually costs only $130. So there's quite a difference in price. It's actually 16 times cheaper. At first sight, it's 16 times cheaper, but you see. This is assuming that we're using, it's only a 6-qubit problem, right? But the Rigetti device actually has 32 qubits. So in principle, what we can do is actually run several instances of the problem at the same time on the chip. So basically running instances in parallel using, chunks of 6 qubits. We could fit 5 of these on the chip at once, of course, because there are 32 qubits. That would so running 5 would only require 30. But what we decided to do was leave a little bit of buffer between, physically on the chip between the different blocks of 6 qubits, just so that maybe it kind of reduced the effect of noise, for example, of crosstalk between anything going on here and anything going on in the neighboring block. So if we run, that allows us to run 4 instances of the problem simultaneously on the Rigetti chip. So in fact, what it means is that we can actually run 64 times the problem on Rigetti for the same price as on IonQ, which is a pretty interesting realization. It's quite interesting, I would say. Quite a dramatic difference in cost. So that means that on IonQ, we're basically going to get one shot at running an instance, our problem instance, right? We're going to be able to run it just once. And it only has 11 qubits. If it had 12, we would maybe be able to run it twice, run 2 instances of it simultaneously. Because it only has 11, we can only run once, one at a time. But on Rigetti, because of the fact we have this 64 fold difference in cost, we can do quite a few more things. It basically means that we could run the same problem instance, but we could pick, say, 64 different random values for all those thetas in our circuit, right? So we initialize them with some values, of course, as is always the case. But we could try, 64 different, completely different random initializations for all of those thetas. So basically, thinking in terms of the cost function landscape would be starting in 64 completely different places, which could help us more effectively find good solutions. It also allows us to explore hyperparameter tuning of the algorithm, of the optimizer algorithm, SPSA. So SPSA has a number of hyperparameters associated with it. you can think of them like, step size, for example, is a common one which is associated with gradient optimizers. So these are the kinds of things that you can vary with SPSA. The hyperparameter we chose to vary was this thing called, well, it's basically it's the magnitude of the initial update. So in the very first step, you have kind of a, what's the scale of the angular update that you would pick. You can actually tune this in the algorithm, and this is the hyperparameter that we chose to modify and explore its effect. Okay, so this is in this slide I'm showing results where we've kind of fixed the this hyperparameter value. So all of the results on this slide just show the effect of just keeping this hyperparameter fixed and just optimizing through the different iterations. So there's a lot going on here. So on the y-axis, this is the cost, right? So this is the cost function, the objective function value. In the conventions that we used, anything that is 64 or below is a feasible solution. Anything above is an infeasible solution. So an infeasible solution would mean that the solution would say there are, objects which are assigned to a particular bin mean that bin is exceeding the weight capacity. So that's a solution to the problem, but it's not feasible because it breaks the constraints, right? A feasible solution is one where all of the bins have at least less than the maximum weight capacity, which was 10,000 in this case. So anything below 64 is at least feasible. On the x-axis, this is just the optimizer iteration number. So you can basically imagine what's going from left to right on the plot is just basically tracking the evolution of how the optimization is going. Okay, so let's start with the results from the Rigetti device. So this is the green curves here. So what we've done is actually to run those 64, as I mentioned, there were 64 random initializations. So we basically initialize all of our thetas 64 times, but in a different way. So they're randomly chosen. And we average the cost function value at each iteration over those 64 independent computations, which are of course being run in parallel in groups of 4. And what we see is actually something interesting, that not much is happening. The objective function is not actually really changing. You can see this green line is kind of flat. So even though we're running the optimization, the objective function is basically remaining what it was at the very beginning when we kind of randomly initialized everything. So there doesn't seem to be much optimization taking place in this case on the Rigetti device. That said, the Rigetti device did find a solution. The best solution found, of course, this green line is just the green line here. I'm not sure if you can see my mouse, but the green line, which is kind of just above 80 on the y-axis, is showing the average from the Rigetti device. The green line at the bottom is showing where the best solution that came from Rigetti was found. So it used 5 bins. So it actually coincides with the classical heuristics that I mentioned previously, which is kind of interesting. And turning to IonQ, this is the orange curves now. So the kind of solid orange curve is showing the exact cost function value at each iteration of the optimizer, and the kind of dashed orange curve is the rolling average over the previous 5 or 10, I think it was, iterations. So it's basically averaging over what took place in the previous 10 iterations at each step. And so what you can see there is that there is clearly optimization taking place, right? The cost function value is decreasing. It starts somewhere around 100 or so in that region. And by the time we get to 100 iterations, it's dropped into the feasible region quite clearly. So it's found feasible solutions to the problem, at least. That's good, right? At least it's finding feasible solutions. The best solution it found was used 7 bins. So it didn't find as good a solution overall as the Rigetti device, but there was clearly much more optimization taking place. Oops, sorry. Okay, the blue curve, by the way, is the result from the simulator, which kind of confirms that our algorithm, well, it is not spectacular, but it is actually optimizing somehow. It's at least breaking into the feasible region towards the end of these 100 iterations, and the IonQ results kind of tend to conform to that more or less. Okay, so yeah, this is the results when we compare the IonQ to our 64 seeds from Rigetti. But what happens when we play around with this hyperparameter value on Rigetti, right? So this is something that you can imagine as a developer you would be doing, right? So you might, today you would do this on a simulator, right? You would play around with different hyperparameter values, and you would try to find the ones that seem to work best, and then you might go off and actually run the best ones on the QPUs to see how well the QPUs perform given the best conditions that you could identify. But in future, if we can do less of this hyperparameter tuning on the simulators because we're considering larger problems, then you're going to have to look at these hyperparameter tuning investigations using the QPUs directly. So this is kind of the motivation for this. So what happens when we vary this initial angular update? Well, we tried 4 different values. The original one was this 0.005, which is this kind of reddish curve here at the top. Of the other values that we looked at, it's clear that for a few values we got better results. So this kind of pinkish kind of curve here, that was a different value of this hyperparameter. It's clearly shifted downwards, so the cost function values are better. There doesn't seem to be a lot of optimization taking place in this case. But for one of them, the yellow curve, if you squint at it, it kind of looks like there might be some optimization going on, right? So it's kind of started up here around like high 80s, and towards the end, it's kind of dropped down towards like low 80s or something like that. So it does look like potentially for one of these values, there is some optimization going on. So that's nice. One final thing that we tried here, by the way, just for interest's sake, because given that nothing is really happening in most of these cases when running on Rigetti, we thought, well, maybe it would be interesting to compare to the case where we just randomly sample. So we don't even try to optimize. We just throw in random angles to the circuit and then compute the cost function value, and then throw in another set of random angles, compute the cost function value. There's no relation between those angles, right? They're just completely randomly chosen. And as you see, this is the blue curve here. There's no real change in the cost function value across those different choices that we threw in. We've just plotted them as if they were an iteration number, but they're not really an iteration number of an optimizer. It's really just set number 1, set number 2, set number 3 of random angles. And it seems like, most of the Rigetti performance looks like it's just randomly sampling, with the exception perhaps of this this yellow curve, which is potentially showing some optimization behavior. Okay, so that's really the end of the talk, actually. I think I could summarize by saying, so assuming you're in this situation where you want to run a quantum computing project or do some kind of quantum computing project, you might be faced with this kind of how do I kind of think about what kind of project this is? Am I doing this kind of top-down approach where the question is more like, here's a very large target problem. How would I run this on a quantum computer? What algorithm would I use? How amenable is it to quantum computing in the first place? Of course, if you're in the industry side of things, you have to think about these economic considerations. You really want to kind of go through those steps that I emphasized before to try to rule out the use cases that just don't seem promising or amenable to quantum computing, because ultimately nobody wants to waste time or money exploring things that can be ruled out much easier just by applying some kind of principled thinking at the beginning. And a very big part of that, of course, is classical thinking about what classical algorithms can do on the same problem today, because that's one of the, as far as we have seen in our experience, is one of the best ways to quickly identify the use cases that are likely leading to a dead end, or the ones that seem to have more promise. And of course, you need to run classical algorithms anyway if you want to do a more kind of comprehensive study and benchmark the quantum, the performance of the quantum approaches to the classical approaches. So you may as well do the work on the classical side in the beginning, because then it helps you do a lot of this kind of this work to rule out the less promising use cases. And on the bottom up side, I think that the interesting message here is that in particular, what I talked about was cost. So you're trying to use devices today to just learn about how they perform, to try to benchmark some simple problems or some simple algorithms. But of course, you are limited in what you can do because the cost is quite high. And as I said, like typically today, you use the QPUs quite sparingly because, yeah, they are expensive. So you would do a lot of simulation work, identify the right conditions, the best conditions for the quantum algorithm, and then go off and run it on the QPU. But that's going to be a challenge when we're running larger problems, right? So push up to 50, 100, 500 qubits, whatever. It's not clear at all that what you can get from a simulator, which is only maximum, say, 30 or maybe 40 qubits, is going to be very indicative of what you would see if you were to run a 500 qubit problem, for example. So simulation is likely to become somewhat less, I think, important. It will retain, of course, a role, but I think it's likely to become less important. And using QPUs will become more common, but therefore it means that we'll have to spend more money to do these kinds of projects. I think we've talked about here the hyperparameter investigation. So this was an example of how cost can affect the algorithmic and prototyping decisions that you can make. But I think there are many places where the cost of quantum computing could be a major limiting factor in what we can actually achieve. There's been a lot of interest in error mitigation techniques in the near term, as a way of basically, we don't have error correction today, but we have noisy devices, and there are these techniques which can kind of somewhat alleviate some of the noise. There are many classes of error mitigation techniques. Some of them rely on just collecting more and more data, and then trying to find more of a signal in the noise, if you like. But if you need to collect more and more data, the cost of quantum computing is high. In practice, an important question to ask: is this even feasible to do this, right? Because the error mitigation part could blow up the budget for the project. Okay, I will stop there. Thanks for listening, and happy to answer any other questions you have.
Thank you, Yuan. So I guess we can take some questions if you have.
Sure. Thank you very much, Ewan, for this wonderful presentation. My question is, although we saw that the hardware from Rigetti was much economical at first, but during the optimization, as you showed the result, it seemed that it's not doing optimization. So what is it actually going on?
Well, that's another question. I mean, I think we would need to dig a lot more into the data there to see if there was something actually going on. But I think, as I showed, the results were kind of consistent with a random sampling. Mm-hmm. So that suggests, again, like it didn't seem to be doing anything more than simply just random sampling. You can ask why was nothing actually happening? I think that's maybe the spirit of your question. That's a harder, that to answer that question would require a lot more work. It's likely not a problem with our algorithm. Of course, I'm not making any claims that this algorithm is fantastic. It was just a vehicle to try to get some solution to this problem. But the simulator and the IonQ device did show that there was some optimization going on, of course. I could speculate that, you could say maybe because we have multiple processes going on the chip at the same time, there's crosstalk, so the errors are high. It could be that the angular updates that need to be made during the algorithm for in the variational circuit, you're updating the thetas in your parameters in your circuit. It could be that those updates are just the delta thetas are so small that for some reason it's just not making any effect on the Rigetti device, either because the angular resolution of their devices is basically not able to take, if the angle is being updated by something that's in the third decimal place, but the device it will cut off anything at the second decimal place, then basically you're going nowhere, right?
Yeah.
That could be another reason. It could just be that it could be noise, that maybe the angular updates are okay, but there's just a lot of noise anyway, so that's kind of washing things out. I think to answer that question we'd have to probably run quite a few more experiments and do a bit more work to dig that out.
Yeah, great.
Yeah.
So do we have more questions? If not, let's thank Yuan for this very interesting talk. And we have around like 20 people meeting in person, so at the UVA, and then we finish a lot of pizza. So,
Nice. Cool.
Thank you, Yuan. Thank you for doing this.
Yeah, no problem. Thank you. If anyone, by the way, if you want to reach out to me, you can just drop me an email. My email is it's ewan@entropicalabs.com. You can also ask Meng for my contact details. I'm happy to answer any questions you have afterwards if you like.
Okay, so I will distribute your contact information later.
Yeah, sure, no problem. Yeah.
Okay. Thank you, everyone.
Yeah, thank you.
Thanks.
Okay, bye-bye. Thanks.
See you, Yuan.
See you. Bye.